If you have more accessible state, so the system will be quickly reach the equilibrium state. The entropy will be increasing. The entropy will be much, much greater than the case which you have a few number of the possibilities. So you need to get the idea that if a system, a physical system, has a lot of energy level or energy state, then reaching the equilibrium state is more easier for that. In social system also, if you have a lot of customers, and if there is a trading between a lot of customers, so the market will be have more accessible state, and the market will reach the equilibrium very quickly. This is the idea of using the entropy for the markets. So first law of thermodynamics, we cannot add more to that. So you need to explain, you need to understand each part of this law. Second law. The second law it's the hardest one, and it says that the change of the total entropy for any system and the nature should be positive. It means that the S final for total system is always greater than the S initial for the system. When the entropy increasing, what does it mean? The number of accessible states for the final should be much, much larger than the initial. So it means that the system is going to have a more possibility. So this altering in the system is increasing in some sense. So omega f total, if we consider s as a function of that, because we don't know exactly what is the form of the s, we just can understood that the f is a function of this omega. We don't know how. For example, linear or exponential, or quadratic or something. So just you can say that the entropy is a such function of the accessible state or the number of the state that it should be increasing function like that. Delta S should be positive. So when you're writing delta S, you needed to consider the whole entropy, so the whole amount of the entropy. So if your system have inner region or outer region, for inner region you can define the S inside, but not easy, not always easy to do that. And for outside you can define S outside, but not very easy. Sometimes reaching the inside is impossible. Sometimes there is a great wall here and you cannot pass the wall. So there is something here like firewall, and you cannot pass that. In physical real systems, you needed some process to enter the internal of the system. For example, in semiconductors, normally semiconductors should not work like that, but it works. So it means that there is a process which connect the outside to the inside. Or there is some physical quantum mechanical phenomena like Aharonov-Bohm effect, for example. This is about that if you put a magnet here, if you make it a magnetic field here, according to classical mechanics, this magnetic field flux cannot make penetration to the inside of that. But you will see some effect of this magnetic field inside this. Inside of this, what does it mean? You can have, for example, a cylinder, and the magnetic field is outside the cylinder or inside, no difference. And you expected that from the electromagnetic, the magnetic flux cannot make a diffusion and pass the surface. But quantum mechanics show you that a little part of the flux can be detected here, or a little part of the flux can be detected here, if you put at the source in right or the left side, or in or outside. such phenomena sometimes happen, but normally we cannot easily go to the inside of the system if you are in the quantum mechanical regime. So you see that how much difficulty we have to define the entropy. So we needed some modeling to make the entropy. And we will do that. About the first law of thermodynamics and the third law, and you can write the third law of thermodynamics, but for us is the most important is the first and the second law of thermodynamics. One thing about that which is not very if you divide that by the delta T, and if you suppose that delta T is positive, you don't have any other possibility. Delta T should be positive. Then if you take the limit of that, you will get the time derivative of the total entropy with respect to the time. Huh? This is called an S dot. There are a lot of activity in the cosmology branch of the physics to check this inequality. If somebody can find a real system with the particles in the cosmos, I mean in the largest scale universe, which violate this law, so it will be very interesting. But so far, I can tell you that, at least in my field, like astrophysics and cosmology, there is no any direct violation from that. No direct violation detected so far. This is one of the fundamental inequality in the whole physics. The time derivative of entropy should be always positive. The entropy never decreases. This is, you know, from the first. But one more thing. The arrow of the time is just to the future. Yeah? Delta T is positive means that the T final should be greater than the T initial. Time never back to the past. So it fixes also, it fixes the arrow of time. Arrow of time can never back. You will hear some things about the, I was inspired to understand about the time travel, maybe some of you. But so far, as the thermodynamic works for us perfectly, and also in the statistical description, it's worked perfectly. We can understood that the arrow of the time is going just in the one direction, so time never come back. So what is calling like the time traveling? Forget about the fiction. It is something to the traveling to the future, not to the past. You never come back to past. So that's even if you accept the general relativity cosmology, and if you accept all the aspects of the relativity, the Einstein theory, and if you consider the time as the not absolute parameter, but as a relativistic parameter, even with others. But this is the important things I want to mention here, that the second law of thermodynamics also fixes the arrow of the time. This is a very lessly introduced in the books. So you have all the material. So this is the review of thermodynamics. So I don't want to go more to the detail, but remain one thing. I introduced for you pressure, volume, entropy, and heat, and internal energy. But